All right. Let me just flip the screen. How does one flip the screen? Go to edit.
That's settings, I thought.
No.
Is it this down here? Nope.
Cash in those.
Oh, okay.
Did you solve and forget?
You can open it. On YouTube Live.
Yes,
That old lady lied to us. Let's chat. And sweet, it's $10. And that flipped the camera. Anyone know how to flip the screen
It's right,
so the
it's right.
words? Oh, it's only flipped for me. Okay. That's annoying. All right, so we're gonna go over the test review. Probably no one will watch this live, but we'll just upload it to YouTube later so you guys can watch it later. So we're gonna work through the the review guide that you guys have in class, and then discuss how to solve the circuit. So what's the first one we're gonna start with, Ben?
So we're doing the actual calculated problems on the end. So like 1 through 10. I think a good review problem. We can start with the op amp. That's kind of fresh. Let's do something old. I'm gonna do a nodal. That's pretty easy. That's got a dependent source though.
Okay.
So number 7
Number 7.
on the sample test.
All right, so specifically, the question says find V out in the circuit using nodal analysis. Nodal is another name for node voltage. All right, so this is number 7. I'll draw a circuit. You have a dependent source with value 2Ix, 2 times Ix. We'll come over, you have a resistor with 1 kilo ohm. You have an independent voltage source with 12 volts. Another 1K resistor. You have another 1K resistor. And another 1K resistor.
Just to make it nasty.
And then V out is right there. So V out is the voltage drop across this 1K resistor all the way to the right. And then Ix, see if this green shows up. Is that a bad color? That works. Is that okay? Ix is going down, is defined as that current. Okay, so using node analysis or nodal analysis, so what the law that you employ using node analysis is Kirchhoff's current law. Okay, so Kirchhoff's current law says that the sum of all the currents at any junction in a circuit equals 0, right? So the step-by-step node analysis that you would take is you identify what your nodes are. A node is just a single piece of copper in a circuit. So a node has 1 voltage on it, right? So if I were to point out the nodes in this circuit, this entire piece right here, that's 1 piece of copper, and it has 1 voltage on it. And if we put the ground symbol on it, then the voltage on this entire piece is 0 volts, right? Here's another piece of copper that has a voltage on it. Here's another piece of copper that has another voltage on it. And here's another piece of copper that has a voltage on it. Okay. So once you identify all of your nodes in the circuit, then you want to give each node a name. So step 1 is to identify all of your nodes. Step 2 is to give each node a name. So we've already given this node a name, which is 0 volts. This node has a name because it's V naught, right? It's given to you that there's V out or V naught, however you want to say it. Let's say V out because it's the output. So there's V out volts between this piece of copper and this piece of copper, and so if this is 0, then it must be that this piece of copper has V out volts on it. Okay. Initially, we would want to give this a name and this a name, but because there's information here about voltage, which is a voltage source, this voltage source tells us there's 12 more volts over here than there is over here. And so if we call this node V1, just being arbitrary, okay, then instead of giving this another name, we know that this node over here has 12 more volts than V1. So in other words, instead of introducing another variable into my circuit, I'm just going to call it V1 plus 12. The whole idea is to, when you're using nodal analysis, is to create a system of equations. And so the more variables you have, the more equations you need, right? So if you have 3 variables, you would need 3 equations. So it's up to you as the circuit analyzer to reduce the number of variables from the start, okay? So you need to, before you just jump in and start making equations, this is where a lot of people make mistakes. They just jump in and start making equations. Before you do that, really look at your circuit and ask yourself, what do I know? Well, if I call this ground, then I know that this is V out. This node voltage is V out. And if I call this V1, then I know that this node must be V1 plus 12. So instead of calling this V2, I'm just going to call it V1 plus 12. You know, I'm being annoyingly thorough right now because it's these initial steps that trip a lot of people up, okay? So now we have 2 variables. We have the variable V1 and the variable V out. And the question says find V out. And so we have 2 variables, so we need 2 equations, okay? So that's where our KCL comes in. In English, the KCL says the sum of all currents at a junction or at a node equals 0. So I just set an equation. So I'm going to use the KCL to generate an equation, okay? So here I'm going to draw my box a little smaller. So at V1 here, so I'm gonna write a KCL at V1, at my node V1, okay? So what I'm gonna do is I'm gonna draw a circle, and we'll get to a supernode later, right? But let's say so. Spoiler alert! You're gonna use a supernode here, but let's say you didn't realize that yet. So I'll pretend like we didn't realize we're going to use one, and then we'll find out why we need one, okay? So I draw a circle at this junction, which is my V1 node, okay? My next step is to I'm going to stand at that junction, and I'm going to create an equation, and I'm going to assume that current is leaving that junction, okay? I don't care which direction current is actually going. For the generation of this equation, in almost an isolated sense, I'm gonna assume that current is leaving. Okay, so to remind myself of that, I'm gonna stand at the junction and I'm gonna draw arrows. I'm gonna draw an arrow going left. Does that green show up? Yeah, kind of. Here, let's do red. Yeah, I'm kind of using red for.
It kind of works. You can green.
Oh, good.
Is it green?
Oh,
Oh,
green.
is it?
That is green.
Oh, pink.
I'll do black. Oh, pink's good, but pink's gonna be like red. Here, I'll do black. So my circuit. So I'm gonna ask myself, okay, or I'm gonna tell myself that current is leaving that junction. So current is going to the left, current is going down, and current is going to the right. Okay. So anytime you draw an arrow in a circuit, that signifies current. So I know then that the sum of all my currents entering and leaving this node, in this case leaving, because I'm just assuming they're leaving, equals 0. So I'm going to write 0 equals, and then I'm just going to take one of these arrows at a time. So I start over here on the left. The current leaving actually has a name associated with it. It's 2 times Ix. Right, so let's write that down. 2Ix. Okay. The current going down here, well, I can do one of two things. I can give it a variable name, but remember that extra variables don't help me because I'm trying to solve a system of equations, right? I already have the V1 variable and the V out variable. I don't want more variables. And so I'm going to define the current across a resistance using Ohm's law, right? Where Ohm's law is V equals IR, and therefore I equals V over R. So the current going through a given resistance equals the voltage across that resistance divided by the resistance. So I've already called the voltage over here V1, and the voltage here is 0. So the voltage drop across this resistance is V1. So the current going through that resistor is V1 over 1K, right? So I'm going to add that in my equation, V1 divided by 1K, where K is 1,000. I like to put 1K as, K is not a variable, right? It's just signifies 1,000. All right, so I have the current going left, I have the current going down. Now I need the current going right. When I look at that, and here's the problem with these independent sources when you're doing KCLs. I don't have any resistance information. All I have is voltage information. My KCL is Kirchhoff's current law. I need information about current. What's my current going this way? The short and sweet of it is I don't know, because I don't know the resistance of that source, okay? So what I'm gonna do then is I get here and I say, uh-oh, I'm gonna draw an X here. I don't know, well, that looks like a variable, but I don't know, right? So whenever you don't know what current is, whenever you can't represent it using Ohm's law, that's a sign that you need to use a supernode, okay? So we've already set ourselves up to use a supernode. So here we have this is a simple node. A supernode, they call it a supernode because it makes the circle bigger. We're actually gonna, instead of having a little circle like that, I'm gonna draw a circle like this that encompasses that independent source, okay? Why do I do that? Because this is a visual thing, okay? Where before I had the circle and I had the arrows, the currents leaving that circle, now I just have a bigger circle and I'm still gonna consider currents leaving that circle, okay? Because this current is inside the node, I no longer consider that. I don't have to. But this current is leaving the node, so I still consider that. So I have that current leaving, which is that term. This current is leaving that node. So I have that term V1 over 1K, right? And then I come over here, and I'll get rid of this box. Right? I come over here, and I'm not quite done yet with this circle. I'm gonna draw my circle all the way. I'm gonna include the junctions, right? And I'm gonna draw current leaving over here to the right, and I'm going to draw current leaving over here going down, okay? So this blob right here represents one node, and it's a super node because it contains an independent source in there. So, and 4 currents are leaving the node, left, down, down, right, okay? For every arrow that I have, I need to come up with a term for current. Okay, so we already have left and down over here. Over here we have current going to the right and current going down through that resistor. So let's go back to this resistor, this 1K here. That current is called Ix, right? So we'll just call it IX. It's already defined as IX. And then the current going right is, we can give it an I name, but like over here where we put currents in terms of voltages, like V1 over 1K, the voltage right here, instead of being V1, we already determined it's V1 plus 12, right? So that's the voltage right there on this piece of copper. Minus, so we're asking ourselves, what's the voltage drop across this resistor right here? What's V1 plus 12 minus V out, right? Divided by 1K gives us our current, okay? So now we have one equation and we have four terms, 1, 2, 3, 4, and we have four currents coming out of that supernode. Okay, we have an extra variable that we didn't think about. We have our two variables, the V1 and V out, but now we have this IX variable. Well, real quick, we should put IX in terms of a voltage, so that way we get rid of that extra variable, right? So IX, when we look at IX is drawn right here. And if we use Ohm's law, then we know that IX is V1 plus 12 minus 0 over 1K. In other words, the voltage drop across this resistor divided by the resistance. So V1 plus 12 over 1K. I'll write that right here. IX equals V1 plus 12 over 1K. And just for completeness, I'll put minus 0 so you remember that it's the voltage drop across that 1K resistor. So if we add that in, if we substitute in, we get 0 equals 2 times IX, which is V1 plus 12 over 1K plus V1 over 1K plus IX, which is V1 plus 12 over 1K plus V1 plus 12 minus V out over 1K. Erase VX there. Okay, so we end up with that equation. So that's one equation, and we still have two unknowns, right? We have V1 and V out. So we need one more equation. Well, luckily, there's another node that we haven't touched yet, and we can do a KCL on that node, okay? So I'm going to erase this box. I'm going to draw a circle at the junction, and I'm going to assume that I can do it with a simple node, right? Now check this out. I'm going to grab my current marker, and I'm going to stand here now. Before I was standing here, now I'm going to stand here, and I'm going to assume current is leaving again. And this is crucial. This is where a lot of people will mess up, is they get confused when they set up their equations for KCLs. They get confused on currents leaving and currents coming in. You need to stay consistent when you're setting up your system of equations. And so if you assumed that the current was leaving at one node, when you go over to the next node, you have to assume the same thing, that current is leaving, okay? This is a little counterintuitive. People are gonna try to fight this. If you fight this, you're gonna get it wrong. Okay, so we're standing here and we're assuming current is leaving. So now I need to create another KCL, but now we're at V out. And then I take each of these arrows, I take it one by one and create a term for it and set it equal to 0, because that's what the KCL tells me. So 0 equals V out minus V1 plus 12 over 1K. That's the current going from right to left. V out minus V1 plus 12 divided by 1K plus, and the term going down for current is V out minus 0 over 1K, or just V out over 1K. So that one's pretty easy. Okay, so now I have two equations and two unknowns, V1 and V out. All right, real quick, why did I not draw a current going to the right?
It's not a complete loop.
It's not a complete loop, right? So even though this is an output, until there's a load connected here, there's no current. There's no current going this way, right? This is just a floating piece of copper. It's just hanging there, and there's not going to be actual current flow. There's voltage there, but there's no current. Okay. All right. So what Ben's doing right now is he grabbed his TI-89, and because this is not a math class, this is a circuits class. we're not being tested on our ability to solve systems of equations, right? And I say that because you've already done the work, okay? So don't. I've run into I've tutored circuits a lot, and I've run into a lot of students who to prove themselves or something they say I'm gonna do everything on paper and I'm gonna solve the system of equation on paper, and then they get the answer wrong, and then they're mad they get the answer wrong. So this is the circuit analysis right here. What you do from this step on is just math, and so you can do, and I don't know if your teacher is going to stop you from doing this, so you have to check, but I'm positive you can grab it, a tool like a TI-89 that has the ability to solve systems of equations with the push of a button, right? So if you're using your TI-89, let's talk about that real quick. I would on paper, I would assign each variable either X or Y, okay? And I like to do that usually by writing right on top of it so that I stay very organized and I don't miss anything, okay? So in this case, what was your X, what was your Y?
My X was V1.
Okay, so Ben assigned X to V1, so I'm just gonna write X on top of every V1 that appears. X, 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 okay? And then Y will be V out, so Y, Y, and Y, okay? And I'll walk you through this TI-89 if you guys have one, because it's awesome. I've had this TI-89 since high school, and I graduated high school in 2006, so I've had this TI-89 I think since either 2004, I think since 2004. this same one. All right, so the way you solve system of equations with your TI-89 is you go to F2 and solve, right? So F2 just brings down a drop down list, and you hit solve, and then you start punching in the equation. And so just start with equation number 1. So it's 0 equals, and then good.
Wrong answer on the key.
There's a wrong answer on the key?
No, I didn't.
Oh,
I was
you're
looking
looking
at
at
the
the
wrong
wrong.
problem.
Okay. So 0 equals, so you just type it out on your 89, and then you have the X, Y, Z variables available, and so go crazy with the parentheses because you want to make sure that the numerators stay in the numerator, right? So open parentheses Y minus open parentheses X plus 12, close parentheses, divided by 1K, 1,000, plus Y over 1,000, Y over 1,000. When you finish, don't hit enter yet. When you finish one of the equations, the shortcut to add another equation is you want to put the word and in. So it's going to be like solve this and this, right? So the shortcut is you hit the second button, the 5 button, 8, 8, and that brings up the word and. Then once you have the word and, then you go directly into the next equation. Hi, honey. So 0 equals 2 times open parentheses X plus 12
I know.
divided by 1,000. Hi. Plus X over 1,000 plus X plus 12 divided by 1,000. Right? Plus parentheses X plus 12 minus Y divided by 1,000. Once you put in all of your equations, then before you close parentheses, before you do any of that, you hit comma and then any of your variable names. So you could put comma X or comma Y. Just do one of them. So I'm going to do comma X and then close parentheses. I'm going to hit enter. And that gives me, when I hit enter, it solves for both variables. So it gives me an X, which is my V1. Where's my black? So it gives me V1 equals negative 9.33 volts. Correct me if I made a mistake. And then it gives me a Y, which is my V out, of 1.33 volts. And is that the right answer?
1.33 volts, yeah.
1.33 volts, okay. So we're done. So again, the circuit analysis, it enables us, the node voltage method enables us to create a system of equations, and then once we have that system of equations, we can just punch it into your favorite math tool, which mine is the TI-89, and then it'll spit out your answer if you did everything right. Okay.
Biggest thing to remember is to always go out of the node. I saw a lot of like the kids in our class, and they were trying to do ins and outs, and it was getting very confusing, and they're getting wrong answers mainly because they were changing the method they were using throughout the entire process. And the way that he just showed you is like flawless as far as when I've used it. So
Yeah.
suggestion.
So if you guys follow the steps the way we did them here, you'll get it right every time. There's no guesswork in it, and don't try to be smart.
Keep it simple.
Just kidding. Just keep it simple. Yeah, you guys are smart.
All right.
So that I took a lot of time with that, but like with if we want to practice more stuff, I won't be as thorough. We'll just crank.
I was
through it.
thinking about just looking at some of the problems and you going, what would you do here? What would you do?
Okay.
Here? What would you?
Let's
here?
do that. Yep.
So maybe try and let's see if we can get the screen on the phone.
Sounds
Show
good.
the laptop itself. And just like walk through it, I guess.
Okay. Oh, you want me to?
Like flip the laptop and maybe like as we scroll through it, so we don't have to draw every single problem.
Oh, okay. Bloop. Let's hang on before you move that. I'm gonna grab Mike.
Your laptop. Yeah. As far as conveying a lot of the material that we need to cover in the time we've got. Just that.
Hi. Okay. Careful. Oh, careful. All right, that one's 27 minutes. So we're gonna start another one up. I'm gonna end this one, and then we'll start another one up right after this.
Make this one kind of
How do we end you? End.